Physics class and science class. Topic of today's physics is electricity, or we start with the first part of electricity, which we call the electric charge. So before we begin, let's have an overview of what electric charge is all about.
This video is on the topic of electric charge. Atoms are made up of protons, neutrons and electrons. Protons and neutrons are found inside the nucleus, and electrons are found outside the nucleus. Remember that electrons are negatively charged, protons are positively charged, and neutrons are neutral. Atoms have an overall neutral charge because there are the same number of protons and electrons in an atom. When electrons are transferred away from an atom, there are more positive charges left than negative ones, and so the atom becomes an ion and it has a positive charge. When electrons are transferred to an atom, there are more negative charges than positive ones, and so the resulting ion has a negative charge. This is a concept that students often find confusing. Remember that gaining negative charge makes an atom or object more negative. When charged particles interact, they follow two simple rules. Like charges repel. So two positively charged particles brought into close proximity will experience a force of repulsion. The same goes for two negative charges, such as electrons. However, two oppositely charged particles, so one positive and one negative, will experience a force of attraction. These forces are non-contact forces because they act at a distance. The unit for measuring charge is the coulomb. Let's take a look at an exam question. A student holds a charged plastic rod near a running tap. The student observes the stream of water bend towards the plastic rod. Which of the following shows the correct arrangement of charges in the stream of water? In each of the diagrams, the rod is negatively charged. Water molecules are polar. That means that they have areas of positive and negative charge. You don't need to know that, but that's how this phenomenon actually works. So we need to choose the diagram that best represents what would happen if a negatively charged rod was held close to the stream of water. Now, we know that opposites attract, and diagram A shows like charges attracting. So that can't be correct. And same goes for answer option C. B is showing a pretty equal spread of positive and negative charges. So that's not really showing attraction or repulsion. So we can also discount B. D is showing positive charges attracted to the negatively charged rod. The presence of the negative charges has caused the water molecules to move so that the positively charged areas are closest to the rod. In this diagram, we can see that opposites are attracted. So the correct answer is D for 1 mark. In summary, charged particles are either positive or negative. Like charges will experience repulsion, and opposing charges will experience attraction. When atoms or objects gain electrons, they gain negative charge, and therefore they become more negative. They become negatively charged. When atoms or objects lose electrons, they lose negative charge. Therefore, they become less negative. They become positively charged. Don't forget to check out all our other fantastic revision resources here at Save My.
Okay, so probably if you didn't hear that part, you're going to hear it, you're going to see it in the video. Okay, so don't worry. Here, the lesson here is that atoms are made up of positive charge and negative charge. Atoms are made up of positive charge and negative charge. We said the positive charge, they found in the nucleus of the atom, while the negative charge, they orbit the nucleus. They orbit, they orbit the shell. They orbit the shell. They are found they are outside of the nucleus and they orbit the shell. So we also establish here that when atoms lose electrons, they become less negative and hence they become a positive charge atom. When they lose electron, they become less negative because number of positive and number of negative, they're equal. That's why an atom is electrically neutral. So when they lose electron, the number of electrons is now less. So number of proton or number of the positive charge ions are now more. So the atom becomes a positive ion. But when electrons when an atom gains electrons, they have more they have more electrons, and so they becomes negatively charged. Okay, atoms are either positively charged or negatively charged, depending on whether they lose or gain electrons. Okay, then we also said that positive charges, they repel each other as the law of attraction and repulsion. That's the law of charges. Like charges, they repel each other, and the unlike charges, they attract each other. And then we also establish some of these things. So this is what we want to go through quickly. We said when you take a look at atoms have positive and negative charges. So objects can be given one of these types of electric charge. Is either the object is positively charged or the object is negatively charged. So when two charged objects are brought close to each other, there either be a force of attraction or a force of repulsion. Two things is certainly going to happen. Either they are attracted to each other or they repel from each other. Now, when do they get attracted to each other? They're only attracted if they have opposite charges. If they have opposite charges. Remember, we are talking about electric charge. And electric charge is just the positive and the negative charges that we are described, that are found in atoms. Okay, so when they have same, they will repel. You can see they're drawn away from each other. They will be drawn away from each other because they're same. Same things do not attract. Same thing do not attract. Opposite things can attract. So this and this, they're both positive. Positive and positive, they will repel each other. They will move away from each other. And then negative and negative, same thing. Negative and negative will move away from each other. But if we have a positively charged atom brought together close to a negatively charged atom, they will attract. They will come together and stick with each other. Okay, so these are the overview of the introductory part of this class. We already said that like charges, they repel, and the opposite charges, they attract. The like one, same charge, they repel, and the opposite one, they attract. So these are the law of electrostatic, that opposite charge attract each other, while the like one, they repel each other. Now we say electric charge is measured in the unit called the coulomb. The unit, the SI unit of charge, electric charge is a coulomb. So we write the unit. Okay, so we say charge. What is the unit? Okay, for electric charge, the unit is coulomb. Okay, we say the unit. Unit is what? Coulomb. Coulomb. Okay, just like the way you say the unit of current is ampere, so the unit of charge is coulomb. We normally designate a symbol for charge. We use Q for charge, letter Q. Okay, we use Q for charge, and the unit, the symbol for the unit is C, capital letter C. This is the unit symbol. This is the unit symbol, and this is the charge, the symbol of charge. Okay, electric charge. So we said that the unit for electric charge is coulomb. The unit of electric charge is a coulomb. Is that okay? So here is a brief question before and after, so on and so forth. I think we move on, except we want to see this question and see what the answer looks like. Okay, here let's listen to this briefly. 1 minute.
Let's read through the question together to get a better understanding of what is expected of us here. The diagram below shows two thin plastic strips before and after being rubbed with a dry, clean cloth. The plastic strips were uncharged before the experiment. Using the keywords provided, describe the charge on the strips and the force between the strips. So before we have a look at the key words in the question over here, we've got like charges and opposite charges, or unlike charges over there. We have to choose between those two, and then we need to choose between an attraction force and a repulsion force over there. So we need to just fill in this table. Here we have the two strips in blue, and this is before they were rubbed with this dry, clean cloth. So this is a demonstration. You may have done it yourself in class or in college or in school of electrostatic charging. And then after the charging has happened, you can see that there's been a displacement of the two plastic strips. Let's have a look at the text in the question to make sure we're getting all of the relevant information. So we need to describe the charge on the strips, and we need to discuss or mention or describe the force between the strips. So as I mentioned, this question requires us to apply knowledge on electrostatic charging, and I'm going to bring up a quick screen grab of the basics of electrostatic charging, and that is that like charges would repel each other. So if we had two positive charges, they would be inclined to move away from each other, and that unlike charges or opposite charges would tend to want to attract each other. So if we have a look at what happened, we've got the two strips here, they're quite close together, and after charging we can see that the strips have moved further apart. So we can see that this strip and this strip are being repelled or repulsed from each other. So we can say that the force between them is a force of repulsion because they're moving away from each other. If it had been a force of attraction, they would have moved closer together. They're moving further apart. Because it's a repulsion force, we can say that the two charge or the two strips must have like charges.
Okay. Okay, hello? Okay, hello. So what was there was this question. Okay, you can see the question now. The question was for us to find out two strips. Before they were rubbed, the distance between them was very close. After they were rubbed, the distance rubbed against each other. The distance between them went further apart from each other. So it means the force of attraction is a repulsion force, and charges is like charges. Okay, the charges is like charges. Okay, so that's what we've seen for this case. Okay, for this first case. Now let's take a look at what we have, what is coming next. Okay. Now here is demonstrating electric charges, demonstrating electrostatic charges. Okay, this first part we're actually taking electrostatic. So when we finish this class, we no longer need to do electrostatic. Okay, that's what we're doing right now. So you just a minute and you will see. Don't worry, when we upload the video, you will see everything play for you. So just pay attention.
This video is on the topic of demonstrating electrostatic charges. Certain insulating materials transfer electrons when rubbed together. You may have seen this demonstration done in school. When a plastic rod is rubbed against a cloth, the friction causes electrons to be transferred, resulting in the cloth and the rod becoming charged. In this example, electrons have been transferred from the rod to the cloth. Therefore, the rod has lost some negative charge and become positively charged, and the cloth has gained some negative charge and become negatively charged. Remember that the positive charges in an atom, the protons, are inside the nucleus, so they cannot be transferred. The only way that an object can gain a positive charge is when electrons are transferred away from it. When an acetate rod is used, the electrons are transferred from the rod to the cloth. When a polythene rod is used, however, the electrons are transferred from the cloth to the rod. Once the rod is charged, it will repel objects with a like charge and attract objects with an opposite charge. Exam questions on this specific topic will usually use this context, so make sure you can explain the transfer of charge. Lots of fabric used today to make carpets and clothes consists of man-made fibers, which are essentially plastics and have the same effect with friction. This results in a build-up of charge on the body as you move around in the garment or walk across the carpeted floor. That build-up of electrons has nowhere to go. That's why we call it static. It remains on the surface of the insulator, in this case you, until you touch something that allows the charge to flow, a conductor like a metal. This causes you to experience a tiny electric shock as the electrons are discharged to the conductor. We call this static electricity. This can also happen when you touch another person. The man here has a buildup of electrons caused by his shoes rubbing on the carpet. By comparison, any neutral object will be less negative than he is. Therefore, as he touches the uncharged woman here, some of the electrons flow to her, and they both experience a small electric shock. We can see this happening on a much larger scale in a thunderstorm. Electrons build up due to friction within the clouds, and so the ground becomes positively charged by comparison. As the electrons are attracted to the positively charged ground, they discharge, and this is what we call lightning. Application questions test your understanding of the physics by getting you to apply your knowledge to an unfamiliar context. So it is possible that you could get asked about a different example of charging by friction. Let's take a look at an example exam question. A student rubs a polythene rod with a dry cloth. The polythene rod becomes negatively charged. Explain how the rod becomes charged for 3 marks. To get you started on an explain question, use the words from the question to begin your answer. When you are explaining something, you need to say why it happens. So make sure you include the word because or something similar to ensure that you are fully answering the question. So the rod becomes charged because friction between the cloth and the rod causes electrons to be transferred from the cloth to the rod. Use the key words from the topic to make sure you gain the marks. The last marking point here is assessing your understanding of the direction of electron transfer, so make sure you're super clear about that. In summary, friction between certain insulators causes electrons to be transferred from one object to the other. When electrons are transferred away from an object, the object loses negative charge, so it becomes positively charged. When electrons are transferred to an object gains negative charge, so it becomes negatively charged. The buildup of electrons on the surface of insulators is called static, and when those electrons are discharged, we call it static electricity. Make sure that you're comfortable explaining the process of electron transfer, both in the context of the cloth and the rod example, and in other similar scenarios. Don't forget to check out all our other fantastic.
Okay, let's move on. You will see this particular video, inshallah, we will play today. Okay, let's move on quickly because this is about 4 minutes, thereabout. So we've looked at demonstrating electrostatic charges. So the first part, we are doing electrostatic charge, okay? So electrostatic repulsion is caused by what? The force between the charges. Actually caused by the forces between the charges. When these charges are same, then they will repel each other. They will push each other apart. When the forces are same, they will push each other apart, right? Okay, when they are same, they will push each other apart. So if I have a positive charge here, if I have positive charge rod and I have another positive charge rod close to it, positive charge rod close to it, what happens is that these two rods will pull each other apart because they have same charges. They will pull each other apart, away from each other. But if we have opposite charge, okay, this is the first fundamental, the rule. if you have opposite charge, positive charges here, and then you have another rod with negative, this one they will pull it towards each other. They will pull, the two objects will pull towards each other. They will pull towards each other, so it will come close together because they have opposite charge between the two rods. Okay, so this is one thing we need to get clear. So when these charges are the same as each other, they will repel, they will push apart. But if they're different, they will attract each other. So in ordinary experiment, the production of electrostatic charges by friction is related some solids such as plastics give you a charge. So some plastics, if you're looking at basic electrostatics, you take a pass, you take a polythene, you have to give which one will be positively charged, which one will be negatively charged. So we have to give charges to them if they are different material, plastic material, like a pass and a polythene. So, and then we will, on that basis, model the experiment and give our outcome. So if we want to see the method, what is being done, how we charge by friction, then we follow suit. So what we're doing here, we want to charge by friction, right? We already used the cloth to rub against that material, the two materials. So we bring this other glass towards the plastic. You see it will be drawing it to the direction of the rod, okay? To be drawing it to the direction of the rod. So without touching, just bring it close, and then you see that, or even if you touch a little bit, you see that it will be turning towards the direction of the material that you brought close to it. So what we are saying here is that you suspend one of the insulating material using any stand, rotor stand, cradle, and length of a string, like you've seen just now as we've demonstrated, okay? And then you let it to rotate freely, okay? You let the material to rotate freely. Now you rub one end of the material using a cloth, a piece of white cloth or a cloth, okay, in order to give it a charge. Because if you rub it with a cloth, that material, you're actually giving it a charge. And now take a second piece of insulating material and charge it by rubbing with the same cloth, with the cloth also, right? Then you hold the charge rod of the second piece close to the charge rod of the first piece. And then you see that if the first piece rotates away, if it's away, that means it's repelled from the second piece, then the material have the same charge. But if the first piece moves towards, or that means it's attracted to the second piece, it means the material, they have opposite charge. So this is an experiment on how we demonstrate charges, how we demonstrate electrostatic charges. And then here is a question demonstrating charges also. Here we're looking at the electrical quantity. So let's listen to this and get a grab of it.
Let's read through this question together to make sure we understand what we have to do to answer this one. In order to demonstrate how to produce an electrostatic charge, a student wants to rub a rod with a cotton cloth. She can choose any two of the 4 rods shown below for the demonstration. Which 2 rods should she choose? Explain your answer. So let's have a look at what we've been given. There's a copper rod, a glass rod, a plastic rod, and a steel rod, and we need to choose which 2 of these the student should be using to demonstrate this process of electrostatic charge. So let's just highlight the key phrases in this question. So we need to choose 2 of the 4 rods, and we need to explain our answer. So we need to choose which 2 rods will produce an electrostatic charge. And the process we're going to use is this process of rubbing the rods. And we're going to rub the rods with a cotton cloth in this case. So this is a question that's based on an experiment or a demonstration that you should be doing in your class or in your college or in your school around electrostatic charging. And here's a screen grab of that. So we need to be able to explain in an exam how to perform a demonstration like this. But the notes are quite insightful in that it mentions here how we give an insulating material a charge by the process of friction. So we've got 4 different types of materials here, with steel, plastic, glass and copper, but only 2 of these materials are considered insulating materials. Copper and steel are conductive materials because they can conduct heat and electricity. So rubbing these with a cloth will only achieve a nice shiny surface, not necessarily, or it won't give us any kind of electrostatic charge. So we're rubbing them, so we're meeting the requirement of friction, and we know that it's those 2 because those are the only 2 of the 4 we've been given that are actually made of insulating materials. So let's just build a short, succinct answer for you here, and here's our answer window. So the first thing in my explanation is I'm going to state that there will be friction between the cloth and the rods. That's what this rubbing is going to do. Further, I'm going to say that only the insulating materials can be charged by friction. We can't charge the copper and the steel rods by friction with a cloth, it should be said, with a cloth. And then lastly, the glass and plastic rods should be chosen as these are insulating materials, and the part in brackets is just completing the answer because the copper and steel rods are conductive, and here I've circled the 2 correct answers.
Okay, this question was actually to test the 4 materials were given, as 4 rods were given: copper rod, glass rod, plastic rod and steel rod, and then the students rub them with a piece of cloth. They say which 2 can produce electrostatic charges. Remember, electrostatic charges are only found in insulating materials, not in conductive material. So copper is a conductor, so copper is out of it, copper rod is out of it, and steel rod is out of it because they both metals and they conduct electricity directly. You don't need to rub a piece of cloth. But for electrostatic generation, you need insulating material like the glass rod and the plastic rod. So these are the only 2 rods that qualifies for this question. Is that okay? So we move on to the next one as fast as we can. Now we're going to electric field. Okay, now we're looking at electric field, and let's have a brief about electric field. Okay, we can just move ahead and so that we save time. And so electric field region in space where the charge experiences a force. The region in space where a given charge, maybe a positive charge. The region in space where this charge experiences a force. Okay, this charge will experience forces in all these directions. Okay, a region in space where a charge experiences a force is called electric field. A region in space where a charge experiences a force is called. So this region, okay, this region around here, all this region, okay, in space where this charge can experience force is called electric field. It's called what? Electric field. All this region where the charge experiences a force is called the electric field. So electric field is a region in space where a charge experiences a force. Okay, a region in space, a region in space where a charge experiences a force. where a charge experiences a force. Experiences a force. So that region is called the electric field. It's called the electric field. Is that okay? That region is called the electric field. Okay, so when we talk about electric field, we are referring to the region around a charge, the region around the region in space around the charge where it experiences electric field. Remember, for positive charge, the field moves away from the charge. For negative, the field comes towards the charge. So a charge object creates an electric field. Every charge object creates an electric field around itself. Every charge object creates an electric field around itself. And this is similar to the way in which magnet creates magnetic field also. Okay, magnetic field is the region in space where a magnetic pole experiences a force. So it's the same way we define electric field. Where we say in electric field, we say it's the region in space where a charge experiences a force. In magnetic field, we say is a region in space where a magnet or where a pole experiences a force. Okay, so the field lines always point away from the positive and always points towards the negative. The field lines points away from the positive charge and points towards the negative charge. So these are electric field. All these lines with arrow, they're called the electric field. They're called the electric field. So electric fields are always directed away from positive charges and towards the negative charge. They are always directed away from the positive charges and directed towards the negative charges. Now, the direction of the field lines in electric field is described as the direction of the direction of the force. Okay, the direction of the field line is the direction of the force on a positive charge at a given point in time. For example, if the field are coming towards the negative, it means they're coming from the positive charge, and that's why they are entering the negative. If the field lines are entering, in negative, the field lines, they just come inside. Where are they coming from? They're coming from the positive charge. So we can put a small plus here. We're saying that they're coming from the positive. They're coming from the positive. They are coming from. So if they are going away from positive, we say they are going to the negative. They are going towards the negative. Okay, that's the direction. They are going towards the negative. So you see here, the direction of the force is what? The force is entering the negative. So the field lines show the direction that a positive charge will experience if it was at that point. A positive charge will experience if the positive charge was brought to this point. If it's brought to this point, it means it will go this way. That's the direction of the field lines. Okay, that's the direction of the field lines that we are seeing. How much of the field lines we have shows the strength of the electric field. If you have very few field lines, like 4, 1, 2, 3, 4, it means that's the strength. If you have 6, it means the strength of the electric field is way more than that of 4. If it's 8 field lines, it's more than that of 4, and it's obviously more than that of 6. So the strength of electric field is how much of the field lines we can see that is going towards or away from the charge. So the pattern, okay, the pattern we see for objects in electric field, we experience an electrostatic force. That's already established. A force, every object you bring close to any electric field, the object will experience electrostatic force or kind of force. So if you bring a piece of paper towards a pen that you rub against your hair, the piece of paper will feel some kind of force. So if you bring any object towards any electric field, then the object will feel some kind of force. The force could be attractive force or it could be a repulsive force depending on the material you brought close to it. If the material is same as the charge on the field, then it will experience a repulsive force. If it's opposite, then it will experience an attractive force. It will experience an attractive force. Okay, so this is exactly what the size of the force depends on the strength of the field. If you want to see the size of the force that is produced, the size depends on the strength of the field. So if the field is strong, then the force produced will also be strong. Okay? Okay? Then we say this means that the force becomes stronger as the distance between the two charged objects decreases. When the distance is reduced, the force produced will be stronger. If you bring any object close to the charge, then the force will be stronger. If you take it farther away, the force that is existing between the charge and the object will be weaker. Okay, this is a normal relationship. Field lines around a point charge. We've already established that if you have a point charge like positive charge or negative charge, for positive charge, the field lines will emanate from the positive charge in all directions. We go away from the positive charge in all directions. For negative charge, we will come into or towards the negative charge in all directions as well. Okay, they will come into or towards a negative charge in all directions. We also go to look at uniform electric field. Okay, we also look at uniform electric field. So we already said if you have around a point charge, the field lines around a point charge, is that for this the field will move away from the point charge. The field lines will move away from the point charge, right? They will move away from the point charge. The field lines will move away from the point charge. Move away from the point charge for positive point charge. Okay, for positive one, the field lines will move away. The field lines will move away from the positive point charge. If we have a negative point charge, the field lines will move towards it. If we have a negative point charge, the field lines will move towards the negative point charge. The field lines will move towards the negative point charge, okay, as we've demonstrated right now. The field lines will move towards the negative point charge. Field lines will move towards the negative point charge. Okay, don't mind my drawing. The field lines will move towards the negative point charge. The field lines will move towards the negative point charge. Okay, this is for a unit point charge. That's number one. How will the field lines be when you take a uniform field? When you take uniform field or uniform material. So if I take a uniform material, let's say I take two plates. One is positively charged. One is positively charged. How will the field lines be created, or how will the field lines be produced? And this is another negative plate. We have a negative plate, we have a positive plate. Now the field lines will no longer be like this. They will not be like this. This is radial electric field. Radial, the first one, for the first one. The electric field lines produced is called radial electric field. Radial electric field. Electric field. Now, what about when we took two uniform plates? The field lines will travel from the positive towards the negative. The field lines will travel from the positive towards the negative, like this, in a uniform manner. So it will be traveling like this in a uniform manner. The field lines will move like this from the positive side towards the negative side, except in the edges, that it will not be straight. In the edges, it will fringe. This is called fringing. To fringe. Okay, only in the edges it will not be a straight line. Only in the edges it will fringe. I'll write the fringing. I'll write the spelling for fringing. It will fringe. Only in the edges it will fringe. Fringing. Okay, the rest, and this title is uniform electric field. This one is called for, the field is called uniform electric field. Okay, this is called uniform electric field. The first one is radial electric field. The one from a point charge is called radial electric field. This second one from two plates is called uniform electric field. Is that okay? So it's called uniform electric field. So we move on. This is uniform electric field between two parallel plates. Okay, electric field between two parallel plates. Now field lines around a charged conductive sphere. Field lines around a charged conductive sphere. Field lines around a charged conductive sphere. The field lines around the charged conductive sphere are usually symmetrical with a point charge, okay? They're usually symmetrical with a point charge. Now this is because the charges on the surface of the sphere will be evenly distributed on the sphere, okay? The charges will be evenly distributed on the sphere, okay? Even if they were scattered before, they will become aligned to the edges. They will become aligned to the edges. Now the charges are same, so they repel. The charges are same, and then they will repel each other. Now the surface is conductive, allowing them to move. Okay, this is a charged sphere. Normal sphere is like this. Let's say we take a sphere. For normal sphere, we have, this is a sphere. What we have is, we have positive, negative, negative, positive, all spread across here. Positive, negative, positive, negative, all spread across here. Negative, positive, positive, positive here, negative here, all spread, positive here, negative here, positive here, negative here, and then positive here. They are all spread here. So when you bring a charged rod, let's say for example a positively charged rod, if you bring a positively charged rod, then it will attract all the negatively charged sphere to this side, and all the positive will go to the other side. It will separate them, it will arrange them and separate them, to filter them, such that only the negative will come to this side of the sphere. Only the negative will be attracted to this side of this positive sphere rod that you brought to this sphere. Only the negative will be here, the positive will be on the other side. You separate them by bringing an oppositely charged rod towards the sphere. Okay, now this field lines pattern can be demonstrated using a Van der Graaf generator. This is a Van der Graaf generator to generate or to show the pattern of the field lines that are produced. One method uses the streamer is shown. Okay, so these are just basic things which all we need to do now is to see an example, okay, to see how these fields are related.
Here's a question for us to look at. Short and sweet, but let's go through it quickly anyway. Select which of the four diagrams below show the pattern and direction of an electric field between two charged plates. And here we have four diagrams. So these two are relatively similar. These two are relatively similar. These darker lines are the plates, and these have a positive charge on the bottom, negative charge on the top. And it's the same structure of two plates, positive on the bottom, negative on the top. So all four have the same structure. Here I have a parallel pattern where there's a charge running towards the right. Here I have a parallel pattern with a charge running towards the left. Here I have a perpendicular pattern. So when I say parallel and perpendicular, I'm with reference to the plates. Here the charge is going down, and here the charge is going up. This is very simply just a question that requires us to remember what the charge, an electric field between two charged plates looks like. There are three fields we need to remember. One is the field around a single particle or a wire. It's called a radial field. We need to know the charge between two plates, or the field between two plates, my apologies. And then the third one is the electric field between two charged particles. Those we just need to commit to memory and remember. Before we carry on though, let's just check we're not missing anything. So it's just a selection exercise. So it's tick a box, choose which one. Please don't guess which one. You want to guess now, that's fine. But in your exams, please don't guess. Try and apply some of the knowledge you've learned. Looking for an electric field. That's more important than you can think, because these are definitely not magnetic fields. They're more reminiscent of magnetic fields. So they may look familiar, but they're wrong as far as electric fields are concerned. And we're looking for the electric field between two charged metal plates. So it's one of the three we need to remember. So the screen grab I'm going to bring up comes straight out of our theory, and that shows that between two charged plates, so there's a positive plate over there and a negative plate over there, by convention, the field lines will be perpendicular to the plate surface, there it is there, and it will flow from positive to negative. So immediately I'm going to discard these two that look more like magnetic fields than electric fields. If you're not seeing it yet, that's fine. I'm just going to rotate the image quickly for you, just to align it with what we've got in the question itself. So I've got the negative field on top, or the negative plate on top, and I've got the positive plate on the bottom. So that's the same as these two setups. And here we can see that by convention, the field is going to move from the positive plate to the negative plate, and that then meets the requirements of this option down here. So that's going to be our correct answer.
Okay, so with this, we come to the end of this section of the class, okay? With this, we've come to the end of this section. Our next section will be conductor or electricity. Okay, sorry, I think let's just look at conductor and insulator, and then we end the class. Conductor and insulators and electrons, right? So conductors are those substances that can conduct heat and electricity, usually metals. The key difference between the conductors and insulators is that conductors allow charge carriers to freely move about. Conductors allow charge carriers to freely move about, and insulators do not allow charge carriers to freely move about. The reasons for this are to do with their internal structure. That's why insulators do not allow charge carrier to freely move about, and conductors are able to allow charge carrier to freely move about. Now conductors, a conductor is a material that allows charge or electrons to flow through them easily. Materials that allow charge or heat or electricity to flow through them. Electricity means charge. When we say electricity, we are saying the movement of charge. Okay, they allow charge to freely move around them are called conductors. These materials are called conductors. Examples of conductors are silver, copper, aluminum, steel. These are good examples of conductors. Now we have conductors tends to be metals. Now we see here these are very metallic conductors. Then later we are going towards insulators. We have copper is a good conductor, iron is a conductor, carbon is tending to be a conductor. Okay, because graphite can conduct. Water is faintly, but not really. Air is an insulator, and glass is an insulator, and rubber is an insulator. So these are conductors and insulators. Insulators are materials that do not allow charge to flow through them, and they don't have charge carrier to carry the charge to flow through them. On atomic scale, conductors are made up of positively charged metals, ions, with their outmost electron delocalized. They allow delocalized electrons to move about freely. Okay, for conductors. Metals conduct electricity very well. Why? Because they carry the current is the rate of flow of the charge by particles. They carry charge about. They charge carry electrons about, and then electricity is produced in that manner. So the more easily electrons are able to move or flow, then the better the material is as a conductor. The more easily electrons are able to flow in any material, the better the material is as a conductor. Conductors, they have positive charge, they have delocalized electrons that are able to slide past, okay, slightly. So these positively charged metal ions, the big positive charge they are the metal ion, while the electrons are the delocalized one. They are free to move. The electrons are free to move. You can see they have arrow. Only the electrons have arrow. They're tiny, they're smaller, but the positively charged metal ions, they are big and they don't have arrow. Electrons have arrow because they are free to move. They can slide past each other, and this is why a metal is able to conduct electricity or conduct heat, because it has apart from the charged ion, they have delocalized electrons that are free to move, slide past each other. Insulator, on the other hand, do not have these characteristics. An insulator is a material that has no free electron. They don't have these free electrons that are free to move about. Okay, they don't have the localized electrons or free mobile electrons that can move slightly over each other. They don't have that. Okay, they don't have the free no free charges. Insulators are material that has no free charges, hence does not allow the flow of charge through them very easily. They don't have free charges and they don't allow the flow of charge to pass through them. Example of insulators are rubber, plastic, glass, wood, paper, and so on and so forth. Okay, some non-metals such as wood allow some charge to pass through them, some, although they are not very good at conducting heat or electricity or allow charges to pass through them. They do conduct a little in the form of static electricity, just a little in the form of electrostatic. So example of this type is two insulators can build up charges on the surfaces if you rub them against a piece of cloth. If those surfaces touch each other, then they would allow the charge to be carried away or conducted away. Okay, so this is an experiment that is used for investigating the electrical conductor and insulator to see if a material is a conductor, if you bring it to a charged material or not. Okay, this is called the gold leaf electroscope, and it's a device that is used to demonstrate the charge. The gold leaf electroscope consists of a metal plate, such as this. It consists of a metal plate. This one, sorry, the metal plate. Insulated collar, has insulated corner, and then it has a metal rod. This one, this metal rod, and then it has the gold leaf. Why we call it gold leaf electroscope? It has a gold leaf attached to this this rod, this metal rod, and then a glass screen to protect, to cover it up. Okay, so this is what it consists of. It has a metal rod. At the end of the rod, a very thin leaf, gold leaf foil, is attached to this metal rod. Okay, a gold foil leaf is attached to it, and then the rod is held by insulated collar inside a box with a glass sides, allowing the gold leaf to both be seen and protected from drought. Glass is to protect it from drought or to be seen. When the gold leaf is charged, the plates, rod, and the gold leaf have the same charge, either positive or negative charge, both of them. So when you charge the gold leaf electroscope, the plate, the rod, and the gold, this plate, this rod, and this gold, they all have the same charge. They all have the same charge. Either they are both positive or they are all negative. Now, since the rod and the leaf have the same charge, they will therefore repel each other, right? Since they have the same charge, the leaf, the metal, the rod, and the metal plate, since they all have the same charge, they will therefore repel each other, right? They will repel each other, and the leaf stick out of the side. When the rod and the leaf are discharged, meaning they are neutral, the leaf hangs down. The leaf will hang down. When they are discharged, when there is no more charge, this leaf will the gold leaf will hang down, will no longer be stretched out like this when they are discharged. Is that okay? Okay, so how do you test for electrical conductors and insulator? Charge the plate of the gold leaf electroscope so that the gold leaf stands clear of the rod, right? Okay, these ones we can always, these are normal things. They carefully touch the plate of the gold leaf electroscope with the items being tested. For example, metals such as wire, paper clip, scissor blade, and or another thing, non-metals such as paper, finger, glass, graphite. There, plastic, you can also tell for plastic such as plastic ruler, the handles of scissors, the finger of plastic sandbags, and so on, sandwich bags, and so on and so forth. Now you record the observation in each time. The leaf falls, material is a good conductor. Leaf remains in the place, object is poor conductor, that's insulator. So these are the things we do in this regard, okay? So before we go, we give example of conductors, metals and graphite, example of insulator, plastic, glass, and most of the non-metals. Okay, so this is all we have for this section. Next session we take current electricity. So we're done with electrostatic current. We're done with the electrostatic current.